Okay. So we start with the garnet zone. So garnet zone is in the range of the lower amphibolite facies condition, right? So which is in 500 to 550 or 600 degrees centigrade, or even 500 to 550 degrees centigrade, where the first garnet appears in the rock, right? As we discussed in the zone concept, that new mineral obviously appears, but the older minerals which were already there, they also continue to coexist. Okay, they may continue to coexist, or they most of the cases continue to coexist along with the new mineral, which is garnet. So garnet in a pelitic rock appears in the lower amphibolite facies conditions, okay, with the temperatures around 500 to 550 degrees centigrade. So when you find garnet in the rock, you know that you have already entered the amphibolite facies condition. Now the question is, what are the reactants? What are the reactions which leads to the formation of the garnet? So if you see that it is dominantly the reactant is the chloride. Okay, you see out here chloride, chloride, chloride. Even if you don't remember the exact reactions, but what you see, the dominant reactants are the chloride. Along with that, what you need is quartz. Quartz is common. Some places there is muscovite. So what you need basically to form garnet is the chloride. What does chloride contain? It contains iron, magnesium, and aluminium. Okay, and if you uh, and you add some silica, what you form is garnet. Okay. Also, what you see, muscovite also contains potassium and aluminium. So if you have potassium, the garnet doesn't take any potassium in its structure. Therefore, you have to form some biotite as well to balance for the potassium which is there in the muscovite. What is also more interesting to note is that chloride is the reactant, which means that chloride is all chloride which is present is drastically reduced at the beginning of the garnet zone, which is the lower amphibolite facies, to form garnet. Okay, so when garnet appears, chloride is practically gone, and water is on the product side, which means that chloride is a hydrous mineral where there is water, and water is released, so that as you form garnet, the rock is becoming more and more anhydrous. Garnet is an anhydrous mineral. Water from the chloride is reacting to form garnet, and the water is released, so the rock is becoming more and more anhydrous. Okay, so this is what you need to understand from these reactions. The very important thing is the mass balance. So if you understand, or if you remember what are the components in these each mineral, you will understand the background of these reactions. Okay. Okay. So tell me, what is almandine garnet? You have done it in mineralogy, right? This ALM represents almandine, PY represents pyro. So what is almandine garnet?
Sir, Fe will be present. In pyrop, Mg will be present.
Okay. Along with Fe?
Sir, Fe,
Can you say the
Fe,
formula?
yes, sir, Fe3, Al2, SiO4 3.
Okay. So basically, this is iron aluminum bearing garnet, and pyrope is magnesium aluminum bearing garnet. So a solid solution between that, we call it a pyrope almandine garnet, where FeMgAl is present. Okay. Okay. So H2O is released in most reactions. So bulk slowly becomes less hydrous. Okay. Chloride muscovite decreases. See, chloride is definitely the most important reactant because you need iron and magnesium to form garnet, which is an iron magnesium mineral. Muscovite is also takes part in some of the reactions. So chloride definitely and some muscovite decreases and consumed in the reaction. What is increasing is biotite. If muscovite is consumed, biotite increases. Okay, so chloride and muscovite decreases, biotite increases. So this is what happens in the temperature range of 500 to 550 degrees centigrade in the lower amphibolite facies conditions. Okay, therefore the common rock type definitely is garnet muscovite schist, less biotite. And if there is less muscovite, we call it as a garnet biotite schist. Now, depending on the prevalence of the cystose mineral, we name it slightly differently, obviously. So if there is prevalence of muscovite and less biotite, we got it as a garnet muscovite schist. Why? In majority of the cases, or in all cases, in fact, garnet forms as a porphyroblast, right? Garnet forms as a porphyroblast, so therefore the garnet, according to the nomenclature, comes first. Muscovite is the cystose mineral, which defines the cystosity, and as it is a cystose mineral, we call it as a schist. Okay. Most of the times, in 99% of the cases, these rocks or these metamorphic rocks are accompanied by deformation, which means that the cystose minerals align themselves in a particular direction to form a foliation. Okay, therefore we generally get a schist. Okay, if the biotite is more, we call it as a garnet biotite schist. If both are equivalent, we can call it as a garnet muscovite biotite schist as well. Okay, so depending upon the modal proportions, this would be the common names, commonly schist in the garnet zone. Okay, any questions?
Uh, Sir, is there any preference among these three reactions, dominating reactions, sir?
No, there is no really preference. It depends on the compositions. Okay, so if you have an iron-rich chloride, okay, and so this would be the
Yes,
preferred
sir.
reaction. Okay, if you have a chloride which is both iron and magnesium rich, then this is number one and number three is practically the same reaction. You can see that it depends upon the composition of the chloride, that what would be the composition of the garnet. If the chloride is iron magnesium rich, then the garnet will also become iron magnesium rich. If the chloride is iron rich, then the garnet will also become iron rich. Okay, so 1 and 3 is
Yes.
practically the same reaction. And another reaction is where muscovite is a reactant. In 1 and 3, only quartz along with chlorite is a reactant. In number 2, along with chlorite and quartz, muscovite is also a reactant. The difference is that in this reaction you form biotite. The other two you don't form biotite because you don't need to. Okay. Now depends on the slightly difference in the bulk composition. If the rock has a lot of muscovite, then the muscovite reaction will be slightly more preferred. If the rock has relatively less amount of muscovite, then the muscovite less reaction or this other two reactions will be relatively more preferred. But normally what happens, all these reactions take simultaneously or takes place simultaneously.
Okay, sir.
Okay. Okay.
Yes.
Okay, so these are the pictures. This is how a garnet biotite muscovite schist looks like. So the one practical that you have done for the metamorphic rocks, right? So this is practically the garnet biotite muscovite schist. That is what you have seen. Okay, if you remember, the rocks were practically very similar to this, right? Only that we had more prevalence of muscovite than biotite. Do you remember?
Yes.
Okay, so that had more muscovite and less biotite, but this is how the rock looked like. Okay, so if you look at the, for example, if you look at this rock, this you can clearly see that the amount of muscovite is more because this white musco. Have you seen muscovite or biotite in hand specimen? Do you know how they look like?
No, sir. Hand specimen, we don't.
Or in a rock? Have you seen it in a rock? Unfortunately, probably no, right?
No, sir.
Means have you
No, sir.
taken a rock on your in your hand ever which contains, let's say, biotite or muscovite?
Yes, sir.
Uh,
I have taken.
Yeah, okay, some special cases, but in general I'm saying in class you did not get a chance,
No,
right?
sir.
no, sir.
No, sir.
No,
No, sir.
Okay, yeah, that's kind of very unfortunate. Means I really feel bad about it, but this is how the situation is. Means you as a geologist or an earth scientist, it is very unfortunate that we are trying to teach you petrology, mineralogy without being able to give you a chance to hold a rock with your hand. Okay, that's the unfortunateness of the situation. Unless you hold it, see it with your eyes, these photographs always will remain as photographs. Okay, so the feeling of it, the how it looks like when you see it with your own eyes, directly the sample, that creates a much long-lasting impact. Yeah. Nevertheless, let's see if you people can come back or when you will come back. So if you are interested, you can always have a look. We can show it in the lab. Okay, but yeah. So what you see out here is a rock and muscovite. If you see, check out pictures uh, on the internet, you'll see that it is a silvery kind of mineral. Okay, and if you put it, if it is in the rock, then the shining nature, what you see in this rock out here on the left, comes. This is typically from muscovite. Now, biotite doesn't have this shining nature. It is in the hand specimen, it is brownish in color. Okay, so if you have a rock, brownish, or in fact, more commonly, it becomes really black. Okay, if you take single flakes of biotite, then sometimes it may feel brownish, but a combination of several flakes will always look black. This biotite, flaky in nature, black in color. So if you have a rock full of biotite, that rock will completely look black in hand specimen. Okay, so this is typically a garnet muscovite schist, and you see these red things out here, red minerals, right? Do you
We
see
can
these
see
red
that.
minerals? Yeah, these are the porphyroblastic garnet. Okay, so these are the porphyroblastic garnet. Now, if you cut this out, make a thin section out of it, then you get something like this. Here, obviously, the biotite is more. You might get even more amount of muscovite out here, a muscovite dominated rock, similar to that what I showed you in the practical class. Okay, so I do not know what the situation would be, but in fourth year you are entitled to go to a field, but I'm not really sure that how the situation would be, whether it would be permissible to take you to the field or not. But there, that's a very excellent opportunity where you really see the rocks in the nature, and it gives a what to say, a much better impression of the situation or of the studies. Okay, so let's see. I really do not know.
So, sir, where we generally go for field trip?
We normally go to there's a place called Ghatshila Galudi in Jharkhand. Okay, so near Jamshedpur. So those who are from Jharkhand would know or nearby areas. So that is the region where we normally go for and the field trip.
Oh, okay, sir. So that way, that is a structural geology field trip or a petrology?
This is the first year where the course has changed, where it will be a structural geology and petrology field trip. But whether we will be able to go, I do not know. But previously, this field trip was in the third year, where it was more structural because the students did not know petrology at that point. Okay, so obviously, as you can understand, even if the rocks don't understand what is structural and what is petrology. Okay, all the features you see it in the rock. Okay, so if you take a rock, if you observe the rock in the field, you will find them folded. You will find all the features of the structure, as well as this is a rock. Okay, majority of them metamorphosed rocks, some igneous rocks as well. Therefore, you can always study the aspects of petrology on the same rocks as well. And that was the idea, to combine this field and bring it to fourth year, that you study the background theory for both structural and petrology. And when you see the rocks, you don't have to wonder that what kind of rock is it and only look at the structural features or the other way around. You look at the rock only from the petrological point of view and do not observe any structural features. So to avoid that, we clubbed it and brought the field trip to the fourth year. So this would have been the first year where with structural and petrology field trip together.
Yeah, okay, sir.
Okay, anyways, let's move on. Okay, so the next is the staurolite zone, right? Now, staurolite is a mineral which appears in the middle amphibolite facies, as you can understand, in the range of 550 to 630 degrees centigrade. Okay, and it is, as you can see out here, it is an iron, magnesium, aluminium, dominantly iron, magnesium, aluminium silicate. Okay, so this staurolite normally occurs as porphyroblast in the rock. If you look at this, this is the mineral staurolite in a rock. Okay, and below it is a thin section where this typical blue color, yellow color is of staurolite. Okay, these grains are staurolite. It is porphyroblastic, but the characteristic yellow color, and it is also very strongly pleochroic. That is the typical of staurolite. Okay. Now what you see is that this is the index mineral in the staurolite zone, which means that the staurolite appears in the rock, but garnet, biotite, muscovite, quartz, plagioclase, the previous garnet, biotite, at least the previous minerals which appeared in the previous zones, are also prevalent in these rocks in the staurolite zone. What is important? Chlorite is completely lost, which means that as long as there is chlorite in the rock, okay, as long as there is chlorite in the rock, it will react with quartz and muscovite to form garnet. Okay, so in the in the garnet zone, chlorite is completely used up to form garnet. And biotite is normally more in proportion than muscovite. As you have seen, muscovite is also lost in the reaction. So muscovite takes part in the reaction and forms biotite. So dominantly what you have is garnet, there is staurolite, and there is muscovite. Obviously, I don't say that all muscovite is lost, but majorly there is more muscovite more biotite than muscovite in the staurolite zone. Now, if you look at the reactions, okay, if you look at these reactions, that dominantly garnet plus muscovite gives staurolite, biotite, quartz, and water. If by chance for some special kind of bulk composition, chlorite, or some grains of chlorite is still left out, this also takes part in this reaction to form staurolite, biotite, quartz, and water. Okay, so that's why I marked it in red. Normally, chlorite is completely lost, but if a few grains are present, this will be taken up in this reaction. But dominantly, what you see, there is garnet plus muscovite. So whatever muscovite is present now reacts with garnet to form staurolite. Okay, as in the garnet zone, there is much more garnet which is present. Muscovite is lost much more. Therefore, what you see is that formation of staurolite and more biotite. Okay, so the rock increases in staurolite and biotite. So the prevalence of biotite increases and biotite becomes a dominant schistose mineral in these rocks. Okay, and again, what is important, what you see is that muscovite is lost, which means that there is a lot of dehydration. Although staurolite is also a hydrous mineral, there is dehydration, which means the rock is becoming more and more dry or dehydrated, less amount of hydrous minerals. Okay, so the dominant features to remember in this reaction that there is a strong dehydration and there is consumption of chlorite and muscovite. Chlorite is completely gone normally, muscovite is consumed in the staurolite zone, and biotite becomes the most dominant schistose mineral at this stage. So what we normally see is normally a staurolite schist or staurolite garnet schist, depending on the mineral assemblage. Okay, if both staurolite and garnet are present, we call it as a staurolite garnet schist. If it is only dominantly staurolite, then we call it a staurolite schist. Okay, similar to garnet, staurolite also acts as a porphyroblast. Therefore, it is well, a staurolite garnet biotite schist or staurolite biotite schist also we can call. There's no problem to denote that biotite is the dominant schistose mineral out here. As garnet, staurolite commonly acts as a porphyroblast, like what you see out here. Okay, any questions? So this is how a mineral, big mineral of staurolite, sometimes it has twins, and in a normal thin section, this is how you see staurolites looking. Okay, these yellow ones are all staurolite, these ones are garnet, and you can many places see the staurolites around garnet, which means that garnet is taking part in the reaction of staurolite. Okay, and this is, as you can see, some schistosity by these elongated minerals. These are dominantly biotite. So this is a garnet staurolite biotite schist. Okay, yeah, this is commonly how it looks like. Obviously, different textures can be, but this is how you see a garnet staurolite schist or a staurolite garnet schist. Okay, any questions?
So can you please correlate the Muscovite, when you were telling about the garnet zone, you told that they have more of potassium in the Muscovite, and that has a special impact there. And here we have Muscovite, and here the same potassium is not having major impact. That is just getting converted into biotite.
No, I did not say anything, the major impact on that.
Sir, in the garnet zone,
In which zone? In the garnet zone.
garnet, yeah.
What did I say? I did not follow. What you wanted to say?
Uh, Sir, I think before that you said somewhere that Muscovite has potassium, and there you had emphasis about something about potassium. So I
No,
really
emphasis means out here. If you can see this reaction as well, that muscovite out here is the potassium bearing mineral taking part in the reaction, right?
yes, sir.
Now, garnet, which is forming from chlorite and quartz, okay, does not have potassium in its structure.
Yes, sir.
So what it has to form is biotite, the
Yes,
other
sir.
mineral which takes up potassium. This is
Yes,
what
sir.
I
Yes.
said. Okay.
Okay.
So
Okay, sir.
to form this reaction, to continue with this reaction, we need one potassium to balance two sides of the reaction that you have done in chemistry. To balance potassium on the left hand side in the reactants, okay, you have to have a potassium bearing mineral on the right hand side of the reaction as well.
Okay, sir.
Now we
Same
do
thing.
not write all these reactions in terms of their formula because it makes it look very complicated. But you can, and we have not really balanced it out here just to show what are the reactions taking place. But if you try to write in terms of the formula of the chemical formula of these minerals and you balance it, you'll see that potassium is on the left side, so you have to have potassium on the right side as well. Okay,
Yes,
simple
sir.
mass balance. Okay, now we move into the kyanite zone, which is in the range of 630 to 700 degrees centigrade. Okay, one thing what you should notice out here is that within the amphibolite or within the range of the amphibolite species, you see at least three new minerals appearing. You see biotite, sorry, you see garnet, okay, you see staurolite, you see kyanite. at least 3 different index minerals appearing, and there is a pretty much change, quite a lot of change in the texture and the mineralogy of the rock within the range of pressure temperature condition of the amphibolite facies. Okay, this is the beauty of the pelitic rocks that we started with, that this is a special family of rocks or a special composition where you see a lot of change in the mineralogy with change in pressure and temperature. So looking at the rock and the mineral assembly, you get a much better idea about the pressure temperature condition of metamorphism compared to that of the mafic rocks, where, for example, in the amphibolite facies, the entire zone is dominated by plagioclase and amphibole. Okay, but you see much more changes, which means that these compositions, this bulk, the pelitic bulk composition, is more sensitive to pressure and temperature compared to that of the mafic rocks. And that's why, to determine the pre-T conditions of metamorphism, okay, this pelitic rocks gives us much better information compared to that of the mafic rocks. Right? Agreed?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
so you see that a new mineral, a kyanite, has appeared, and the previous zone, the staurolite zone, garnet zone, previously biotite zone, all these minerals are also present. Quartz and plagioclase is already there, plus minus muscovite, as you can understand from the previous, that muscovite is constantly, if you look at the garnet zone, okay, muscovite is being consumed. What you are forming is biotite. If you look at the staurolite zone, the reactions, muscovite is being consumed. What you are forming is biotite. Now if you come to the kyanite zone, what you see is that again muscovite is being consumed if it is present. So there is a constant decrease of muscovite, and muscovite is constantly taken up in the reaction. And biotite, as of now, none of the reactions have taken biotite, which means that biotite did not react. Only new biotite has formed from muscovite. So muscovite is practically changing to biotite, or the potassium content of the rock is transferred from muscovite to biotite. Right? Agreed?
Yes, sir.
Okay. So
Yes.
if muscovite is still present in the rock, then the staurolite reacts with muscovite and quartz to form kyanite, garnet, biotite, and water. If muscovite is not present, okay, so staurolite and quartz can directly react to form kyanite, garnet, and water. Okay, so what is again you see the reaction on the reactant, if you have muscovite, on the product you have to have biotite, because these are only 2 potassium bearing minerals. If you don't have on the reaction side muscovite, then you don't form biotite, you form only kyanite and garnet. Again, what you see, water is going out, you are slowly forming minerals which are all anhydrous. You have kyanite, which is anhydrous, staurolite is slightly hydrous, garnet, which is anhydrous, quartz is anhydrous. So you are increasing more and more anhydrous minerals where water is being released. Okay, so if you, this is practically the path, if you look at on a kyanite, sillimanite, andalusite path, so this is roughly the path we are talking about.
Hello, sir.
Yeah, just a moment, let me finish. So this is roughly the medium PT path that we are taking, and which actually moves from the kyanite to the sillimanite zone. So we are now in the kyanite zone, and therefore kyanite is stable and kyanite forms in the reaction. We will now move to the sillimanite zone, where we will see that the sillimanite is forming. Okay, yeah, Aditya. Yeah, Aditya.
Yes, sir. Sir, in the kyanite zone, if uh, 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 rock will be again, if in the kyanite zone, if the minerals will be again metamorphosed from low PT condition to the high PT condition, but in the same kyanite zone, then what changes will occur?
I did not understand. So in the kyanite zone, what we see is that if you are in the temperature range of 630 to 700 degrees centigrade, kyanite starts forming.
Okay.
Yeah. So that is it. So you have a rock which had staurolite, garnet, biotite, quartz. When you reach these temperatures, these minerals together start reacting. Okay. These reactions are temperature dependent. So staurolite and muscovite would start reacting. Okay. So unless you reach these temperatures, staurolite and muscovite coexist with each other in the staurolite zone. When you cross into these temperature zones, then staurolite and muscovite do not coexist with each other and they have a reaction relationship. And therefore, they react with each other, the staurolite with muscovite and quartz, and the staurolite with quartz to form kyanite. So, as we move from 630 to 700 degrees centigrade, these reactions will continue and staurolite will be lost and more kyanite will be present or kyanite will appear in the rock. That is the change.
Yeah, yeah. So I just want to know if the product mineral, suppose a if the rock is consisting kyanite, garnet, and S2O, and it is again it comes under the metamorphism, but the rock will be under the same kyanite zone, under the kyanite zone, then what changes will occur? The mineral
So
composition will be same,
what do you
or
mean by
it will
it is
vary?
already in the kyanite zone? What do you mean by again metamorphosed? If you metamorphose the kyanite, garnet bearing or this rock out here, if you again metamorphose it, means that you are increasing the temperature again. Now, if the temperature goes beyond 700 degrees centigrade, then there will be certain changes in the rock. Right. Either, otherwise, I'm not getting your question.
Yeah, so the temperature range is about 630 to 700 degrees Celsius. So maybe in the first time the temperature is then the mineral changes at 650 degrees Celsius, for example. And if from that position, if again it will come under the metamorphism, then in that case the mineral composition will be same. Higher
So are you
temperature will be
talking about two
within
stages of
700 degrees
metamorphism?
Celsius.
I'm still not getting it. Are you talking about two stages of metamorphism?
Yes, sir. Yes, sir.
Yeah. So if these are rocks are polymetamorphosed, so which we are not discussing at the moment. Okay. If the rocks are polymetamorphosed, now depends on. So this answer cannot be so straightforward because this depends on that what happens to the rock when during the retrogression. So polymetamorphosed means the rock, let's say, reach the kyanite zone or the amphibolite phase condition, then it cooled down, okay, came to the surface or near the surface, and again it got metamorphosed by increasing pressure and temperature at a much later time. So these two should be separated by a large amount of time. So we are not really discussing that stage at the moment. We are discussing in single stage of metamorphism. Polymetamorphism or the effects of polymetamorphism depends on a lot of things, which depends on what happens to the rock during retrogression and so on. So the answer cannot be so straightforward. Okay.
Okay, sir. Thanks.
Okay. So if you look at the hand specimen or under the thin section, so this is now how the rocks looks like. Okay. So these ones, kyanite is on a, if you magnify it, so this looks like this. It has many a times it have this slight bluish tinge. Okay. These are elongated minerals, right, with a light bluish tinge. And these are actually the kyanite grains in the rock. These can be staurolite or garnet. These are the kyanite, and you can clearly see a cystosity or a foliation, which is dominated by these dark colored, and I guess these should all be biotite. Okay. So this is how the rock looks like under the hand specimen. This is a close-up picture of a big kyanite grain. This is how a kyanite looks like, and a normal rock under the thin section. For example, the rock on the left, if you make a thin section, you will find it like this, where you can see kyanite, you can see garnet, and you can see all these brown are biotite, which are dominantly forming the cystosity. Okay, isotropic garnet is isotropic. Kyanite is here in this picture. Garnet looks colorless as well, but normally it is a pinkish, slightly pinkish in color. But kyanite is colorless, and these lines are actually one set of cleavage that you see in the kyanite. Elongated, colorless mineral, very high Ri, and under cross polarized light, this gives variegated third order interference colors. Okay, and you can see one set of cleavage very nicely. So that is how garnet, kyanite, garnet kyanite bearing schist looks like. Okay, so as we were saying, so now if you move along this path, what you hit is basically the kyanite sillimanite phase boundary in this diagram. Okay, so the next is the sillimanite zone. So practically, if we move or cross on from the kyanite zone into the sillimanite zone, this is what happens. So this is where what is the sillimanite zone out here. Okay, so you can see out here along this range, on this medium PT condition, the crossover of the sillimanite to kyanite roughly occurs at around 700 degrees centigrade. And 700 degrees centigrade is the boundary of the amphibolite and the granulite facies. So normally sillimanite, the first sillimanite in a pelitic rock appears in the lower granulite facies condition. Okay, so around greater than 700 degrees centigrade at a pressure greater than 7 kilobar in the lower granulite facies, the first sillimanite appears. Okay, so remember, if you see sillimanite in a pelitic rock, so just a sillimanite in a pelitic rock, you can assume that it has reached the granulite facies condition. It may be lower, it may be higher, that we will come to it. But if you see sillimanite, the presence of sillimanite in a pelitic rock indicates granulite facies condition. Okay, so you have garnet, biotite, muscovite, very less depending on the composition, but what you definitely have is garnet, biotite, sillimanite, kyanite, quartz, plagioclase. Staurolite can be there or may be completely gone. Okay, so what is the reaction? The reaction is basically the polymorphic reaction of kyanite to sillimanite, right? The kyanite changes to sillimanite, but the actual mechanism is not as simple as the reaction implies, as sillimanite is rarely replaced by kyanite. Means it's not that just because the temperature and all kyanite will be immediately replaced by sillimanite. Okay, these polymorphic reactions takes time, and the process is very, very slow and doesn't occur just with the flip of temperature. Okay, so kyanite definitely changes to sillimanite, but kyanite can continue as a metastable state within the sillimanite stability field for a pretty long time. But what is the actual implication of the sillimanite zone is that the newly formed Al2SiO5 polymorph will all be sillimanite. Okay, so we practically have the same reactions as the kyanite zone, where the staurolite, muscovite, and quartz, in place of kyanite, it forms sillimanite, or staurolite plus quartz, which was present from the staurolite zone, forms sillimanite and not kyanite. Okay, so the newly formed Al2O5 polymorphs will all be sillimanite rather than kyanite. There is the application, actual implication of being in the sillimanite zone. So the sillimanite nucleates as fine fibrous needles, which is called fibrolite, on the micas. Okay, so the muscovite, if it converts to sillimanite, so on the micas, the mica and the staurolite, there is sillimanite needles developing on it, and they slowly grow in size with the increase in temperature. Kyanite changes to sillimanite very slowly, and this change of kyanite to sillimanite or forming of the sillimanite This is called the first sillimanite isograde. Now, why is it called the first sillimanite isograde? Which means that there has to be a second sillimanite isograde as well, and we will come to that later. But this is the first time that sillimanite appears in the rock, and therefore it is the first sillimanite isograde that we call. Okay, we don't call these for any other mineral because sillimanite is the only mineral which appears in two different types of reactions in the rock. The first one is the polymorphic transformation, which is just sillimanite to kyanite. Okay. Later we will see that some reactions only sillimanite form, doesn't form kyanite. Okay. So the staurolite is lost by the end of the sillimanite zone. Okay. So this is also important. The staurolite is lost in the kyanite zone, and by the end of the sillimanite zone, it is completely lost. Normally, we do not see a lot of staurolite moving into the granulite facies condition. So staurolite is a mineral which appears in the upper amphibolite facies and disappears or appears in the mid amphibolite facies and disappears in the upper amphibolite facies. It is a typical mineral of the amphibolite facies in a metamorphosed pelitic rock. So now the common rock, the schist grade into gneisses, okay, but gneiss maybe a little bit into the granulite facies, but in general, granulite facies, we will see that as soon as the biotite and the muscovite starts decreasing, the schist is no longer there, and what we form is more of a gneiss. Okay, so the cystose minerals as it starts now, as you can see, when you come to the sillimanite zone, the muscovite is completely lost. The cystosity is only defined by biotite. And the next we will see when the biotite starts getting consumed, then the rock is completely no more schistose, and we see a faint foliation, and it would be a gneiss. Okay, so this is how it looks like. These needles are the fine needles of sillimanite, which are very hard to see with the naked eye, but under the microscope you can see that. And these are replacing the micas, and this is what happens when the first sillimanite appears. As the increasing temperature, these sillimanites grow in size and becomes much coarse-grained minerals. Okay, so this is practically the last where we have the sillimanite and K feldspar zone together. Okay, this is very important. Sillimanite and K feldspar appearing together, and that's why we named it as the sillimanite K feldspar zone, right? So sillimanite and K feldspar occur together only in the granulite facies condition. If you find in a pelitic rock, if you find sillimanite and K feldspar together, it is definitely within the granulite facies condition. Okay, and this is what the mineral reaction is. And if you see in a muscovite dominated rock, this is the first time where K feldspar appears along with sillimanite. Now, at this condition, in a muscovite dominated rock in the granulite facies condition, the muscovite doesn't change to biotite, but it changes to K feldspar, and the first melt appears in the rock. Okay, so this is a hydrous mineral. Muscovite stability is breached, and the muscovite changes to K feldspar, and a melt is produced. So this is the first time in the granulite facies around 700 degrees or more, around 750 degrees centigrade, that the muscovite starts breaking down and the formation of the melt takes place. Okay, so very important. K feldspar was lost in the biotite zone, as I said, in the upper green schist facies, and reappears only in the granulite facies condition. If somebody says that he or she found a K feldspar or K feldspars in a metamorphosed pelitic rock in the amphibolite facies condition, this is a completely wrong, because this cannot happen. Okay, so your theoretical knowledge, the point is that your theoretical knowledge should also guide you regarding the mineral assemblage. Okay, K feldspar is completely lost in the biotite zone and never appears before it reaches the granulite facies condition. Muscovite is, if present, is commonly lost by the above reaction. the minerals which are most prevalent till the sillimanite zone, muscovite plus quartz, are both reactants. You see, muscovite, quartz, and plagioclase are all reactants, are the only reactants, and it is completely lost in the sillimanite facies condition, or completely means muscovite definitely, quartz and plagioclase decreases. What we have is sillimanite K feldspar and the generation of the melt. K feldspar and sillimanite, both K feldspar and sillimanite occur separately in the lower grade. K feldspar in the green schist facies condition, sillimanite in the lower granulite facies condition, occur separately at a relatively lower grade, together only in the mid granulite facies condition. Okay, above 750 degrees centigrade, sillimanite and K feldspar occur together, and therefore this is called the second sillimanite isograde, or the sillimanite plus K feldspar isograde, where sillimanite occurs along with K feldspar. And this is also the reaction where melt appears for the first time in the pelitic rocks from the breakdown of muscovite. And therefore, what we start forming is a migmatic rock where the melting starts in the rock. Okay, so muscovite is lost, and slowly the rock becomes more and more gneissic, and the cystosity is completely gone. So obviously, as you can understand, I said previously a few times that the muscovite may be completely lost. Okay, muscovite is always a reactant, but this reaction always takes place if there is excess muscovite left. Now, muscovite left depends on the bulk composition. If the rock was initially rich in muscovite, then muscovite can still stay at this point. Now, the question is, if the muscovite is not present so far, it is already consumed, then will sillimanite and K feldspar not appear together? Yes, it will appear. We'll just show that the biotite also starts reacting now to form sillimanite and K feldspar, but at a slightly higher temperature. So sillimanite and K feldspar together occurs together by the breakdown of muscovite and the breakdown of biotite to form more and more melt and to form a gneissic rock. So I'm moving a little fast because just one or two slides want to finish off today. So this is how the rock looks like. These are big grains of sillimanite. These are quartz feldspars in the matrix. This is also a big grain of sillimanite. So it's a sillimanite dominated rock. Okay. So K feldspar, quartz are all at least in this photograph we cannot differentiate, but K feldspar and quartz can be here, and these are the sillimanite. And you see how the look of the rock has changed from, let's say, the biotite zone, the garnet to the garnet zone, staurolite zone to this sillimanite K feldspar zone. If you look at this hand specimen as well, the prominent cystosity is gone. You can see a foliation, but it is a gneissic foliation, not a cystose foliation. Okay, so if you now if you look at this graph, what this graph shows that within the granulite facies, starting from around 700 degrees centigrade, okay, at around more than 6 or 7 kilobar. So what are the reactions which are taking place? Okay, what you see is that just if you cross into the 7-8 kilobar, so just above the granulite facies condition, what you see is this reaction, what I just showed you now. Muscovite plagioclase quartz gives aluminosilicate, which is sillimanite, K feldspar, and melt. Okay. The more important is that as you move through the temperature, as you increase the temperature, okay, as you increase the temperature, the other reactions also kicks in, where biotite becomes the reactant for the very first time. Okay, in these reactions where biotite, aluminosilicate, plagioclase, and quartz gives garnet, K feldspar, and melt, biotite, plagioclase, and quartz gives OPS, K feldspar, and melt. Okay, so what you see is that K feldspar, aluminosilicate, sillimanite already there, K feldspar forming. Biotite in these two reactions, biotite is the reactant for the very first time. Okay, previously garnet formed by the breakdown of chloride. Now garnet again forms in the granulate facies, more and more garnet by the breakdown of biotite. Biotite becomes the reactant. The K potassium in the biotite goes to K feldspar. There is a formation of melt. Again, biotite becomes the reactant to form orthopyroxene K feldspar in liquid. So what is reacting or what is forming dominantly is liquid, a lot of melt, a lot of K feldspar, garnet, OPX, which becomes the dominant minerals as you go higher into the granulate facies condition. Biotite is lost, so cystosity is lost. Okay, biotite dehydration reaction, so the cystosity is completely lost. The rocks become dominant in sillimanite, K feldspar, garnet, and orthopyroxene. Okay, there is a gneissic rock, what we normally call as a garnet sillimanite gneiss. Okay, what is the difference with that of the mafic rock? You can understand that in a mafic rock, we also had orthopyroxene, we also had garnet, but the compositions of the garnet would be different from here. What we did not have is any K feldspar in this rock in the mafic rock. More importantly, at around 900 degrees centigrade, the mafic rock does not melt, but melt is a major component in a pelitic rock at these conditions, forming a migmatitic rock, a typical migmatitic rock. Okay, this is what we call as a partial melting in a pelitic rock. Right, this is the melt which gets segregated many times, and if this crystallizes, the melt is a silica-rich liquid. Okay, silica-rich liquid. Okay, this is the magma, if you can say. Okay, so this melt or the magma, it can be lost from the system, it can go somewhere else and crystallize. If it crystallizes, what will form is a granitic rock. Okay, maybe in your geochemistry you have talked about, Sir has talked about an S-type granite. So this would be a typical S-type granite if it crystallizes to form a granite. Okay, so this is what it is. I think this is all you can see it on your own. So this is a typical migmatite. This is how it would look under the thin section about a migmatite where you have a lot of garnet and orthopyroxene. Okay, only this slide, what is shown out here, you can check out. So this is the melt proportion or the melt mode. Okay, and this is the temperature. You can see the different reactions which are shown out here. For example, muscovite breaking down to garnet K feldspar, biotite sillimanite going to garnet K feldspar OPX. So, and you can see that the amount of melt increases with these dehydration reactions. And as you increase the temperature to 800, 900 degrees centigrade, the amount of melt in the rock will be very, very high. This is what is shown in this diagram. Okay, I don't think we have any time to take questions now. If you have any questions, you may obviously write to me or let me know. I can call and explain it to you. But today I have finished. I am still here. If you have another class, you can go. If you have any questions, you can ask me. But we are done with the metamorphism of the pelitic sediments. I request you to go through the books as well. I'll provide the slides and go through the books and understand the concepts behind it. The reactions, you don't have to remember the exact reactions, but what is important to understand the concept of the reaction to see the mass balance changes taking place in the rock. Okay, any questions?